Great. Welcome back, everyone. So now we are ready to get started with the main seminar today, which will be on quantum symmetric pairs and K-matrices by Andrea Appel. Right.
Thank you.
Take it over.
So, thank you very much. Everything okay, great. And then hopefully the microphone is working. And thanks a lot everyone for being here. Thanks a lot for the invitation. My first time ever and loving it. So, okay. So today, yes, we will continue on what Andrea first explained, and which is kind of the motivation. But I will start from a slightly different set of equation, and then I will explain why this is more like my real motivation, let's say. So we start with a function. This is going to be a complex function into and v tensor v. So v is going to be a finite dimensional vector space, and then we said that this function, this is an L matrix. If it satisfies again the quantum universal equation. And this is in v tensor theta. And then as you see, this is exactly as the usual Yang-Baxter. Now we have some parameters appearing, and there's exactly this complex parameter considered here, and the equation is slightly different. So if you forget about the parameter, then you recover exactly the picture that Andrea described for quasi-triangular of algebras. And so now here also this is a function. Again, this is a complex function. So we can also give some adjective to this matrix, and so generally we would say that. So what we do is simply we look at the matrix coefficient of this function, and then according to the dependence of this matrix coefficient on the complex parameter, then we can say that our function, that our R matrix is constant, and this is exactly, for instance, what Andrea was describing before. Or you can say that this is actually a rational function, a meromorphic function, a formal function, if, for example, the dependence on the parameter is formal, so we have some power 6. Right? Okay, and then similarly, we say that a function k that now goes, again, would be my operator in one leg. This is going to be the K matrix, and this is the K matrix. If it satisfies the reflection equation, so this was the Baxter, and now I will have my reflection equation, and then I never get the parameter correctly, so it's better if I just copy it. And so this will be like that, and this is going to be equal to. Okay. And this is going to be in and v tensor 2 as well. Okay. So actually, this is something that depends on the choice of a solution on the Yang-Baxter. So it's some kind of secondary equation. And again, there is this dependence on the spectral parameter, which is kind of important to notice. What you should see here is that, okay, let you comment. So as in the Yang-Baxter equation, these indices were clearly, we're saying, where we have an operator in two legs. And so when I act on a triple tensor product, then I'm saying these two legs will be first and second, first and third, the second and third, and so on. And then similarly, there would be here, I have an operator in one leg, so K2 and K1 means I act on the second and the first copy. But also, there is this operator here, which is RW over Z to 1. So this, what does it mean? It means that I take my V tensor 2, I flip it, I act with R, and then I flip it back. So this is what this 2, 1 is. And what should we observe in this equation that in a certain sense doesn't necessarily appear in the constant equation? So here again, if you forget about the parameter, then we recover the reflection equation that Andrea wrote. But we should start observing that the K-matrix actually does something weird about the parameter, because here we have this R matrix is just Z times W, and then now here it returns to be W over Z. So something is happening to the parameter, and also this is R W over Z, but 1. Okay, so the point is that from a certain point of view, as I will explain a little bit later, the fact that actually there are this particular interaction of the parameter is essentially what requires you to consider the famous psi that Andrea used in the definition. What does it mean that there is this psi? It means that something happens when you act with the K-matrix. So again, where these two equations come from? They come from, again, from particle physics. And so the situation is that we have some particle moving along a line, and then some integrability conditions given by this Yang-Baxter equation when I have an open line. And then if I decide that my line actually stops at some point, so you may remember from statistical mechanics, generally we do something, we take particles, and then we put some periodic boundary condition. That means eventually everything runs over a torus. And then instead of having these periodic boundary conditions, I decide that there is an actual boundary condition. That means more or less that there is a wall. Then at this point, there is also this reflection equation appearing. So here is really that you have something like your particle bumps against the wall, and then something happens to the particle. And now again, reason why is there this psi? Because again, the idea is that this. Just a second. Yes, sorry.
Just a quick question.
Yeah.
So in the right side of the reflection equation, the K2, should it be a W maybe? Because otherwise it seems to be not very symmetric.
Thank you. Right, even though there is Z and Z. Yes, this is W. Thank you. And so again, the idea is that if you bounce against the wall, that you're not the same anymore. And so something must have happened to you. And this is what the psi actually is doing. Okay. And so the idea is that okay, we like integrable system and particle physics, but maybe we like representation theory more. And so we want to actually provide a full representation theory approach to integrable system with boundaries. And if we look at the Yang-Baxter equation, this is exactly what Drinfeld did. They started from some work of physicists, and then said, well, actually, you know what? The real way to approach this theory is by looking at quasi-triangular Hopf algebras, and this is how I recovered also many solutions of the Yang-Baxter equation. And so the very first question would be, okay, what is the analog of quasi-triangular algebra? And this was the definition of cylindrical bialgebra that Andrea described. So let me rewrite it again, just because we're going to use it a lot. And so again, this definition actually in part was introduced already by Tom Dick in the 90s, together with Arin Goldenburg also, and then was used by Martina Balagovic and Stefan Kolb more recently in 2016, and then we modified it with Bart in 2020. And now, luckily, I don't have to explain the terminology. So the cylindrical part comes from the fact that eventually we get some representation of this type gray group of type B. And then, as Andrea also was saying, those braid groups can be think of as braid groups, braids living on a cylinder. And so this is why we call it like cylindrical. So here again, the data was the following. We have a quasi-triangular bi-algebra, and then we have psi that is going to be this algebra map, and J Drieverkust. Such that we have this condition that you can write very concisely, which is this a cop psi must be equal to aj. This is the compatibility that we want. And then we have B in A of my quadratic algebra. And finally, we have our K. Again, and this is an element such that satisfies these two conditions. So the first one is this local intertwining condition. And the second one is this coproduct identity. And so here, as Andrea was saying, my upside will always be something like this. And then if I put this condition together, this is very similar to how you would recover Yang-Baxter for a quasi-triangular. You put this condition together, and then what you get is something that looks slightly different than that. So you have also R1 psi, also again always mix up with the indices. Psi 1, and this is A plus psi 2 R. And then here again, this is going to be seen with my. I don't use parentheses, but this is what the element is. So it's upside, and then I flip the two components. So this also, again, is slightly different from what we saw before. Okay, so that was the setting that the algebraic setting that we want, and again a little bit of history and motivation. Basically, Tom Dick at the very beginning was exactly doing what everyone is guessing at first. Psi is the identity. But so indeed, by using psi as the identity, very often the only kind of solution I was finding, there was some kind of central solution, or almost central solution. So nothing particularly interesting, but the idea was the same. It's like he wanted to find some action of this braid group of type B. And this is why actually he was using something like, he was calling this K something like a cylindrical twist. And so we kept the terminology. Then Martina and Stefan, they were also working what we will see in a second in quantum symmetric pairs. And then they noticed that if you want to solve this kind of problem for symmetric pairs, which are special coideal subalgebra of Greenfeld-Jimbo quantum group, then looking always for the identity was too restrictive. So you needed something more. And so what they do is that they relax Tom Dick framework, and they said, okay, you know what? Now I will allow psi to be an off-algebra map. And this is what they have. They have some diagrammatic involution of the quantum group. But they were using off-algebra map. And the point is that then why we still needed to change it with Barth is that we really wanted to get the spectral reflection equation. And if you use an off-algebra map, there is no way that you can get the spectral equation. So we actually needed to relax it even more, and then said, you know what, okay, let's use a psi, just an algebra map, but we're not entirely crazy. And then we said, okay, so let's take an algebra map, but let's try to control it a little bit. And this is what J does. J measures the lack of psi of being, let's say, this is in this case some kind of an anti of algebra map, but it controls exactly this part.
So the original in what Martina and that there was no J.
There was no J and psi was an off-algebra map. Exactly. But again, as I said, if eventually your goal is to look at quantum fine algebra, the representation of quantum fine algebra, you really want to produce that kind of spectral reflection equation. There is actually that setting was not working. There was no way that setting could work. And I'll try to explain in a second.
Yeah, just so with this R to one side, so you just mean the psi's are applied on both legs, or
This one?
yes,
Here, yes. Yeah, I'm just applying to both legs.
to both legs. Okay.
Yeah.
And there's no psi on the last R here. Just
No.
Okay.
Exactly. But so actually, yes, just to comment on that, let's actually, since we will do it anyway in a second, this is just an algebraic picture. But as I said, that eventually, why Drinfeld gave this definition of quasi-triangular by algebras or off algebras? The point was, if you find a solution like that, which is an algebraic solution, then actually any representation is going to give you a concrete metric solution of Yang-Baxter. So the reason of doing it algebraically is then the full category representation becomes a source of our matrices. This is also in a certain sense like I think maybe Weil was thinking about particles. So particles with the category representation is going to be a system of particles, and so that more or less works. Anyway. Okay, so in our case, we have all this data, and then eventually what we want to do, we want to take a representation of A, and then we want to evaluate this stuff. So in this setting, if I look at this particular intertwining equation, and then I want to understand K as a map on a representation, then I will have that my K will be a map from B to B psi as a B intertwining. So clearly you see that when I write here B psi, what I mean is that this is the action on B, pulled back by psi. So I first apply psi on A and then I add. And then clearly now you can see why there are the psi appearing here. So here you apply the R matrix, then you apply, so the R matrix is just flipping the two representations. Then you apply K is moving you to a pulled back representation. So when you act with the R matrix, now there is only one psi. Then you apply another K, and that's it. But here, if you start, you have K, one psi, and a second K, and now two psis. So that's why this changes. Let me also do another interesting comment, is that if we go back to the, so notice here that if I look at this equation, in fact, I have 1, 2, this is essentially the same, and then I have 3, so 3 water. I have actually 3 solutions of the Yang-Baxter equation in a certain sense. These are slightly different, but they are indeed always manifestation of a singular matrix, but they have changed. As algebraic objects, they are clearly different. And this was actually exactly what also Cherednik found in his paper 40 years ago. So when he was writing this system of equation, encoding the integrability of basically particles now bouncing between two walls, and then he found all this system of reflection equation, and it wasn't as simple as the one that I wrote, but in fact this equation they were picturing 3 different matrices, and the equation was exactly like that. But now you will have something like minus minus, minus plus, minus plus, plus plus. So there were 3 types of matrices that will interact into this picture. And so algebraically, this result with psi, it is also more faithful to the original interpretation of Cherednik. Okay. And so finally, let's actually do some example as we were saying. So again, the setting would be the following. So we choose G to be in fact, G would be, in general, would be a symmetrizable Catlin algebra over C. And then for the moment, simply, if you don't know, you just think about your favorite semi-simple algebra, so S2 or S3, S4, whatever. And then to this algebra, then we attach the Drinfeld-Jimbo quantum group of G. And this, as you know, this is an off deformation of UG. And then in our setting actually works for all Q. We can do it in formal parameter. We can choose Q to be indeterminate. We can choose Q to be a generic complex number, not a coordinate. And so this is the guy that we consider. This is very interesting of algebra that naturally arise from some solution of the Yang-Baxter equation, and then conversely this is a quasi-triangular, so it produces an matrix. And this would be my my algebra A, and then I will consider this is a universal matrix. So this would be the quasi-triangular structure that I want. And now, as a first thing, I want to talk about so exactly what this B instead is going to be. So this B G. So this is going to be a quantum symmetric pair. And so again, what is this object? So this B is going to be indeed a deformation of a subalgebra of fixed points with respect to an involution that acts on the B algebra. Again, the first thing you need to think about is the Chevalier involution. So think about SLN and then pick the Chevalier involution as an involution, and the fixed point is going to be SON. So generally the idea would be SON inside SLN. This would be a basic example to think about. And indeed, this would be Lie algebra involution of my let's say semi-simple Lie algebra, or in symmetric in the symmetrical Kac-Moody setting. Well, this would be a so-called involution of the second kind, as it was classified by a work of Katz and Wang in 92. And these involutions and correspondingly these subalgebras, they are classified by a combinatorial datum. So this is very similar to the fact that you would say, well, your semi-simple Lie algebra is classified by a linking diagram. So now instead the datum is a little bit more sophisticated. So what we have here is that we have X. This is a subset of nodes of the linking diagram. Then tau is a diagrammatic homomorphism. So basically, it's going to be some permutation of the nodes that is sort of compatible with the coefficient of the Cartan matrix. And these two data, X and tau, they satisfy a compatibility condition between them. And the compatibility condition is that if I take tau and then I restrict it to psi, then here what's something important that I should say is that the nodes X, this generally something that we call the black nodes of my linking diagram. This will be something of finite. Now again, if you think about the semi-simple algebra, this is an empty condition. But if you think about something more, the point is that the black nodes cannot be an affine linking diagram. They need to be something of finite type. And then what I want is that when I restrict tau to this subdiagram of finite type, then what I want here is something that we call the opposition involution of X. And this is basically what is induced by the action of the longest element of the Wide group of X. So basically, if I have now a finite dimensional Lie algebra, and then I take the Wide group, and now I take the longest element in the Wide group, and now I let it act on the generator of my Lie algebra, and then you would see, or on the roots of my Lie algebra, you would see that what it does is that it flips all positive to negative, but then it's actually flipping simply the indices. So it's just sending everything AI to something on the other side. Okay, so this is something to say that tau alpha I is equal to how should I say? Let's say yeah, is it clear for you what the meaning is? Okay. So this is the condition that we have. So this is something like you take WX and you let it act on alpha I. This is equal to minus alpha tau I. That's it. Whenever I is an element X. Okay. And then I take these two data. And then what I want to do here is that I will use this data to hook up some automorphism of the Lie algebra. And this would be the joint action of this Wide group element composed with tau, composed with omega. So I have Chevalier, diagrammatic involution, and then I have the adjoint action of WX. So here again I should put maybe a tilde, but here the idea is that I should take my longest element, I should write it in terms of triple exponentials, and then I should act by conjugation on the Lie algebra. And essentially, this result by Katzenbach in 1992 is telling you that every Lie involution is basically of this form. So this is eventually why this is the right combinatorial thing, up to internal automorphism.
Sorry, what's this omega again?
Say again? Chevalier. So this is just flipping E and F. Everything with a minus sign. So E goes to minus F, F goes to minus E, and H goes to minus H. And okay, so this is what we take. And so now we still do something more. Sorry, let me do that here. So what I do now is the following. I take CNS. So this will be some tuple of just scalars. So I will have as many. So maybe I should write it as CI, SI, EI. This is a bunch of parameters that we will consider that will satisfy some condition. They're not entirely free, but we can for the moment consider it as being entirely free. And then what I do in particular is that from this one, then if I have something like this, I can think of the tuple C to be something that let's say how do I want to write it, but I can take this guy and then I can write something like add the C as an automorphism of my quantum group. What does it mean? It simply means my quantum group is going to be graded over the root lattice. And so if I get something, so here would be simply that this element, whenever it gets something at C on X and its weight, let's say that the weight of X is alpha I, then this is just spitting out CIX. Okay, it's just some diagonal action that I impose on elements where, since I can take any element in my quantum group and see it as having a degree associated to an element in the root lattice, and so I can extend these scalars in this way. Make sense?
What is the S?
In a second. Yeah, the construction is a little bit cumbersome. Makes sense, but it's very, very step by step. Okay, and so finally, we still don't know what B is. So let's give finally a definition of B, or at least not yet. Then now, finally, I will introduce first the psi. And my psi would be, in fact, this diagonal map at C. Then I will take something that looks like at Sx inverse, and then we have tau and omega, and then this guy is supposed to act on the full quantum group. Now again, this is going to be the Chevalier involution of the quantum group. Tau is going to be the trivial lift of the diagram automorphism to the quantum group. This at C is what I just explained, and then this guy is a quantum Wie group operator. This is given in terms of Lustig break group action. So basically, Lustig break group action was exactly a way of taking the triple exponential in the Lie algebra and lift it up to the quantum group. So now we do exactly the same, and we take this complicated object. Now we take this map that doesn't look nice at all, but you're perfectly allowed to consider as an example X the empty set. So this object almost disappear. And then you take, for instance, you can also choose tau to be just the identity, and you're back to your Chevalier involution map. So as I said, the basic example is going to be psi the Chevalier involution, and similarly, my classical Lie algebra, for instance, in type A being SOM. Okay. Okay, and so finally, what we do? We take we finally define some element in the quantum group. So Fi plus psi inverse Fi plus Si inverse. And this is where the other S's come from. Now notice that indeed my psi depends on C, and this other extra term depends on S. So these are the parameters that I get. And then simply my B, which in theory depends exactly on a lot of data. This is this is the subalgebra generated by the BI with I, let's say, I can also take everything, but in fact, I will also consider all UQGX that sits inside the quantum group. And then in fact, I also need some extra Cartan pi, but let's forget it for the moment. Okay. And what you can do, so this clearly, this is an off subalgebra inside the quantum group. So in terms of the coideal property, this gives no problem. This is an off subalgebra. It's a diagrammatic subalgebra. And then you can take this expression and you can play with it. And actually you can see that now the BIs, they also satisfy some coideal property. So that eventually this, I would say this is probably going to be less there. We have the B is a cordial. So B is not just a coideal, but it's exactly as I said before. This is a coideal subalgebra that is a deformation of the enveloping algebra of the fixed points with respect to theta. Where notice that if I take psi and then I send Q to 1, I just recover. And so whenever you take this expression and you send it at Q to 1, this term disappears, and this becomes F plus theta F. Theta is an involution, so this is actually fixed points. And this generates everything. Okay. All right, so there is still a piece that is missing, and this is related to actually my side. Now, if you look at this, actually, you can convince yourself quite easily that this is a group-like element, C at least. So this guy is at C is an off-algebra map. This is an off-algebra map. It's a diagrammatic involution, and then omega is an anti-off-algebra map. So if this term was not here, I would just be able to just consider J equal to 1 with respect to my setting. Whenever I have J, I need to control this guy because conjugation by this is not an algebra map. But this is easily computed. So what you get is that your J in my setting is simply Rx. So this is actually some, let's say, a time modification of the R matrix of UQGX. So this is really what we get.
So just to see, so if we go to SL2, looking at the non-standard Polish.
Yeah.
In that case, what does everything reduce down to? Is that easy to see? Or there?
E plus F. That's it. Like a polynomial algebra generated by one element. So this is what you would call SO2.
Mm-hmm.
So, but this again, so it's polynomial and so on. But then again, if you look at in the quantum group of SL2, this is still surprisingly interesting object to consider itself.
But then that would be for the non-zero S. For the non-zero S, then
For the the S's, I see.
that's
So-
the definition.
No, this is what you remember. I told you that the parameters are not completely free. So generally, for instance, you really don't want this guy to have a component along the identity. Would be not nice. You really want to land it in the Lie algebra. And so generally your S's will be some quantum numbers, which on the other end, or they can be, for instance, some expression of a form of Q. Okay, this is if you're working in Q being an indeterminate, and so we can make sense of this. But eventually will be something that disappears at the classical level, something like Q minus Q inverse. And then you have that. So this term is just gonna vanish here.
So answer would be as if we could see that's the way.
Okay. So should I use this or fine? Okay. All right. And so again, we have okay. So this is our setting now, and everything's kind of so we have the full counterparts of my definition of cylindrical bialgebra with respect to the quantum group. And now we have our first theorem, which says, again, this is something that goes back to Bao and Wang in 2013, and again, Martin and Stefan, Balagucci and Kolb in 2016, and then me and Bart in 2020. And the theorem is very simple. It's just saying that there exists a unique element of the form K equal to 1 plus the sum. Again, this mu, when I say mu greater than 0, I mean that these are elements into the root lattice, into the root lattice, but in fact I can say something more. This will be elements that you can prove to be invariant element into in the root lattice. So this simply means that they satisfy theta mu plus mu equal to 0 of something like that. And this is going to be an infinite series. So I can think of this infinite series as living into something like QQ n plus mu. So I'm just taking the subalgebra generated by the EIs into the quantum group. And then I take some sort of some graded completion of this of the positive part. and this is where this element lives. So it's something here, and this is an element such that, well, now we can say quite shortly. So we have UQG with the universal R matrix with my QSP psi j and k, and this is cylindrical. So this is an example exactly of some stuff that satisfy all the action you have seen before. And again, basically the construction of this element K was done by Bao Wang in a special type, in a special QSP for in type SLN and finite type SLN. Martin and Stefan generalized the construction to arbitrary type, and so this element was still there, I mean, as it was here. But the point is that, again, since they were not really using the formalism that I use with Barth, they were unable to conclude that this is a K-matrix as I want it to be, because the definition of a K-matrix, as Andrea explained, something that categorically is very obvious what it's supposed to be. So some kind of action of the break group is to satisfy the kind of relation. So the guess is very easy. But since they were doing it with this extra restriction of having phi to be an off-algebra map, they couldn't really find that kind of relation. So this object, they were calling it a quasi K-matrix. Because if you look at this theorem, this theorem is just an obvious counterpart of Lustig theorem on the construction of the quasi-R matrix. On the other hand, so the construction that Martin and Stefan did of this element indeed was true for any cat-smoothie, but again, their framework was not adapted. It was not correct in a certain sense to just go to other types. So they were concluding in our paper, they have this remarkable paper, and they were concluding it by just modifying this object by some other operator, but this other operator was existing in something that existed only in finite type. So the result was only for finite type quantum group. They could extend. And so this very basic observation that we did with Barth is just forget about having a diagram automorphism or an off-algebra automorphism, just allow a more general map. This allows you to conclude that what these guys were calling the quasi-K-matrix is a perfectly honest K-matrix itself. And also this construction works automatically, no restriction on the type.
So here in the classical limit, so Q going to 1, you get K equal 1, I guess.
Yes.
So we are back to the setup that we had previously, where we said you get such a K-matrix if you set K equal 1, J equal to R, and psi equal to identity.
Yeah. Yes. I should say, actually, this is not entirely true. Situation is a tiny bit more complicated. And this is very interesting point, but this is technical. I can maybe tell you a little bit later. But another thing is that we work with this system of parameters that is very general, and the theory that we get is not really a symmetric pair, but it's something that Barth and Vida Stregerski, they call a pseudo fixed points of algebras. So it's a slightly more general theory, which generalized that of symmetric pairs. And so one theorem that we have with Barth is that whenever, and this is kind of interesting because it's at the classical level, whenever we're working with an actual symmetric pair, the limit at Q to 1 of this object is going to be 1. But when you work with something that is not a symmetric pair, but is in this other part of this other class of more general pseudo fixed points algebra, as they call it, the limit of this is actually the exponential of something. So it's some non-trivial operator, not even at the classical level. The interpretation of that is not actually still not clear to us.
So this would correspond to a central element or not central?
Is not central anymore.
Do you have the same issue if you consider the H-bar setting or?
Yeah. This is just a classical limit thing. It's not. You can do formal or indeterminate is the same. Okay. And just a word about the proof of this. So basically, this again, as I said, this is a very nice parallel with Lustig theorem on the existence of the quasi-K matrix. So what do? Well, you simply look at the intertwining equation. That you have. And now you impose that you're looking at solution of this form. Now you look at this intertwining equation, you start to hammer it as much as you can. So that actually from this, you can extract a system of recursive equation that then you prove to be consistent, and the normalization condition at 1 is telling you that the solution exists and it is unique. But it's very brutal. I mean, very sophisticated because it's like in Lustig theory. So if you ever saw his proof, it's like there are all these Q derivation that you use it in on the quantum group, and here you get something similar. So something of the similar flavor. On the other hand, it's very, very computationally intense proof. So yeah, so some part that is somewhat still missing in the theory is that you may know that when we talk about the universal matrix for quantum group, then Drinfeld tells you that this is simply the canonical element of the pairing between the positive and the negative Borel. So it's a very conceptually, it's a very straightforward object, and this kind of interpretation we still don't have it. We have something more. Okay. Okay, and so I want to say maybe another thing about again the advantage of our setting with this all this data. And the point is the following. The point is that there is something that we like to call kind of a gauge group acting on this set of data. So we start here, and then we assume that psi, j, and k with respect to our QSP or with respect to our coideal, this is a solution. This is a cylindrical structure with respect to that particular coideal. And then now what we see is that we can take basically we can take any I would say not even an invertible element of my algebra, but initially, if we go back to my first definition in A and B, we can think about G being an invertible element in my algebra. And then I have some kind of action on this tuple. And what do I get? Well, simply what does it mean is that now I can modify these three data simultaneously, getting something slightly different. So here, for instance, my psi becomes a G composed with psi, and then my J becomes some gauge Drinfeld twist, and then K simply becomes GK. And this is still, if this is a cylindrical structure, then this is also a cylindrical structure. So basically now I can play, and I have all these equivalent structures. They are all equivalent, so why should I care? The reason is that there are something slightly different that you're doing on the various pieces when you move one of these G's inside. So for instance, here, yes.
What is G?
G actually, yeah, I didn't say it, but at the beginning now you can think of it. Let's say we're doing quantum groups. You can think of it as being just some example of an invertible element, but now actually this can be done in some, yeah. And the point is that here I just want the adjoint action by G to make sense on my algebra, which obviously here makes sense. This is fine, but now from the point of view of representation, now I'm acting on the representation with J. And similarly here, I'm acting on the representation by J. So if I play with this G, well, here now I need, for instance, something to make sense on the representation. And so let me give you more or less the example. The example actually comes from the definition of psi that we started with itself. So remember that originally my psi was this add C add Sx tilde tau omega. So clearly you see that immediately using this kind of construction, I can take those guys and take it out from psi if I want. But if I do that, remember that this object, this Lustig operator, makes sense only where my representations are integrable. This is the same reason why the triple exponential in the algebra makes sense only on finite dimensional representation, but it doesn't make sense on Vermas, for instance. So if as long as I do this, my solution, I didn't say it before, my solution makes sense on any category O representation. So let me swap it for a second. So if I look at this, even though this series is infinite, the weight of this series is increasing. And so if I act on whatever Verma or highest weight module or something that lives in category O, then this series always truncates. And so it does make sense on any category O. But if I start now, for instance, playing with something like Sx, then this instead is something that makes sense only on finite dimensional or integrable modules. So in this case, for instance, I have various settings that I can consider. So I can start with the original twist operator, and then my construction K makes sense in category O for UQG. Okay, so these are category O module. Again, weight modules with some cone condition. But then I can start to take some stuff out. So for instance, I can take all the things that I said before, and then I can actually consider as psi, I can consider just tau omega, very simple twist. But if I do tau omega, then my new K-matrix is going to be something which is multiplied by a Lustig operator. And the Lustig operator makes sense, Sx. So this is going to be more or less something like Sx times my previous K. And this object now makes sense only on some category O modules, which are integrable over UQGX. So I'm restricting my category to make sense of this. And again, there is something more that I can do in finite type. In finite type, I can actually play with another Lustig operator. And if I play with that Lustig operator, which I add here, and then I use it to modify my psi, then I will have that actually my psi becomes tau eta 0. This eta 0 is this opposition evolution. For UQG. Remember, this is only finite type. So actually now this becomes indeed that this is an anti isomorphism, and this one instead becomes indeed an off-algebra map. So I can modify it in this way. And then now my K-matrix, well, it makes sense only on O integrable representation. And then actually, by the way, if I do this here, then actually my J becomes simply the universal matrix, which is indeed a twist between the coproduct and the opposite coproduct. So psi is an off algebra, but then I twist by R, and so actually I'm twisting by J is giving me the co-opposite of this. Does it make sense? So, but the point is that it's interesting to play with this structure because now I can, if I play with the structure, I can get something better on the side of psi. So I can get something which is a little bit nicer and more appealing than this very complicated psi we start with, but we pay a price, and the price is that our category is getting smaller. The category, for instance, when we really get some solution of the reflection equation is actually getting smaller. So there is some sort of very nice interplay between this data and what we really want to do on representation.
So if in the second case I look at the category, I could put on quantization, for example, GK modules, right? Because it will be finite of finite out with respect to K. And in this setting, will you get something interesting with this K matrix as a limit? No, this is exponentials or
So this will be still infinite type, you mean? Yeah, I don't know actually, to be honest, to do some particular case, if there are solutions that you can describe more explicitly, this in particular sense, I'm not sure. I don't know. I haven't done it, but I'm very ignorant of a lot of literature, and maybe that someone has done it instead. Okay. All right. So now let's try to go back to the original picture.
okay. All right, I'm showing you how that.
Okay.
No,
still is very nice. Okay, that's it. Okay, so what we want to do now, as I said, is like, okay, fine. So now we know that we have a constant solution, but now let's try actually to finally get the final answer. It would be okay. So can we get this spectral solution? How does it work? And so in order to do that, this requires us to consider not just a K-smoothie, now we want an affine algebra. And then a finally algebra, this is going to be, this is a special case of a Kac-Moody algebra. So in Kac-Moody, you have a first class, which are finite dimensional simple algebra, semi-simple algebra, these are all Kac-Moody. And the next class are these affine algebras, these are infinite dimensional. And eventually, they correspond more or less to some loop algebras. So the Lie algebra structure would be something like Laurent polynomials valued in G. And then there is also a central element that we add. And in order to really have a Kac-Moody realization of this object, in fact, we should also consider a derivation, which on the other hand, we now discuss. You can try to ignore it. Okay, so these affine the algebra. So as you see, there are these three pieces that are here, and then similarly, you can do the same for your quantum loop. So now you also have this is going to be the Dirichlet-Jimbo quantum loop associated to my G hat. And then really, when you look at that, remember that C and D, these are part of the Cartan that lives in the quantum loop. So basically, I do the same. So here I don't want to consider D, so I discard it. And here as well, I consider the full Kac-Moody quantum group, and then I forget about D. And then eventually, what I do is that I really consider the quotient with respect to the sector. And this is what we call the quantum loop algebra, which is really a quantization of this part. And again, in a certain sense, we are not doing anything very, very complicated. For instance, in SL2, you take a Cartan matrix, and then your Cartan matrix is going to be slightly different than before. And you have, so this is going to be 2 minus 2 minus 2, 2. This is non-finite tuck. This is exactly S2. And you will still have a generator E0, F0, E1, F1, and with the usual relation according to the coefficient of this Cartan matrix, and you cook up a quantum group. And this is a very, very huge beast. That again is giving a quantization of this. Okay. Now, what happens and why these representation, these objects are kind of interesting. So here there is a nice phenomenon that happens, is that these quantum groups, they have two very different theories. So on one side, I can consider, let's actually go directly to the integrable. I can consider also something like category O, but let's do basically category O integrable module, and this will be with respect to this the Kac-Moody theory that will tell you to consider this representation. This is a very nice category. This is a semi-simple category. Everything breaks down into irreducibles. The irreducible are labeled by dominant weights. So everything will be great. Everything is semi-simple. But those guys, they are all infinite dimensional. So they are going to be still quotient of Fermat's, but they will be very big quotient still. On the other hand, if I decided to forget about my D, so this category O that I have here, this actually is with the D. Can I go a little bit over? Thank you. So if I forget about my D, then I discovered that this algebra actually has a lot of finite dimensional representation, which here we have none. Here we have only trivial finite dimensional representation. That's the only one that we have. But if I forget about the D, then I have a lot of finite dimensional representations. And then while this is a very famous theorem by Drinfeld and Cherry-Presley, and so while here irreducible in category O, they are labeled by dominant weights, then in these finite dimensional representations, they are actually labeled by some P, when these P are essentially tuples of some polynomial. So I have actually a very big, so in this case, actually, to be honest, I should say that the setting really here should be something like that. We're really starting to think about Q being a number. And then in this case, you have that all these irreducible are labeled by tuples of so-called different polynomials. These are polynomials with simply when you evaluate at 0, they give you 1. So the constant term is 1. And so you see, here we have something that still is countable. Here we have some uncountable family of irreducible. Also, this category is semi-simple. This one is not. This category is braided. This is not. So there are in fact examples of representation that you tensor them in one way and they are not isomorphic to the representation tensor in the other way. So the category can't be a braided category. Okay, so it cannot be. So what do you do? I think it's fine. So the first thing to observe will be like, okay, what do you mean these are not, this is not braided? I mean, we do have an R matrix, so it must be. And the point is kind of simple in certain sense. So the R matrix, you remember, this is something of this form. So here there is some Cartan correction, some Cartan part, and then in fact now here I will still have something like this. And this also leaves in some completion, let's say this part at least, this leaves in some completion of UQ and minus tensor UQ and plus minus. Okay, so this is something that grows with the weight. Now, this always makes sense in category O because when you take two tensor product, sorry. So whenever we have a tensor product of modules in category O, then clearly there is always this weight condition. So this is always gonna die, and so this is always gonna be a finite sum. But in general, I don't know what to do. Why? Because this finite dimensional representation, they are not highest weight. They do not admit something that is highest weight. Generally, if you do SL2, you will have, for instance, that E1 is going to act like an E, so it's always pushing you up, but E0 is going to act like an F, so it's pushing you down. So the positive Borel is never going to act locally important. So this condition doesn't work. So what do? Well, you do something kind of easy. In this affine setting, there is one particular node that we denote by 0, which is the affine node. And then we consider something that is called the gradient shift. And the gradient shift is simply something in a variable z that just shifts you up in the z direction only if you are in the affine node. And then you can imagine actually this is compatible with Chevalier, so it means on the Cartan part you're not doing anything, and then the F part you shift by z to the -1. So this is what you do. So now you define Rz to be simply the shift applied to the R matrix. If you do that, you're applying your shift here, so there will be increasing powers of Z appearing on the right-hand side. And so this guy now is sitting into UQG hat tensor 2 formal power series in Z. I'm shifting this leg. Whenever I shift here, I get something that is Z to the height of the weight move. And this actually keeps increasing. And so you get a formal power series. Okay. And then this guy now, you can let it act on a finite dimensional module. Although the action is formal. So generally we have this VZ that we define to be simply the pullback of a finite dimensional representation via this gradient shift. And then now at least we see that the R matrix that before was an actual braiding now becomes a formal braiding. But there is something we can say about this formal braiding. So for instance, here there is a theorem given by Greenfeld and Charlie Presley. And this is saying, for instance, that if you consider this tensor product, this is generically irreducible. And being generically irreducible, it means actually that if you evaluate Z to a complex value, for almost all complex values, this is an irreducible representation. So as you see, the theory is drastically different with respect to that one, for instance, of SL2. When you tensor 2 representation, and these are always irreducible. In this case, here instead, generically, this remains irreducible. And so in particular, what does it mean? If you do that, it means that your operator Rz now decompose it. Sorry, this is generically reducible whenever B and W are irreducible. Of course, otherwise it doesn't work. But so here what happens is that if now I evaluate on these two modules, then this guy is gonna be also I can write it in this form. Where now f is in fact a meromorphic function, so this is a scalar operator, and this operator here is instead a rational R matrix. So it means this is an operator, and the entries of this operator are rational functions. So in particular, I can distinguish a finite number of poles. And this finite number of poles, they correspond precisely to the values where this representation breaks down. Okay, so sorry, let me try to finish. So here the first thing is that in fact, if you have this spectral R matrix that we construct this way, we evaluate on finite dimensional module, we recover solution of the spectral Yang-Baxter equation. This was the original Drinfeld theorem. And then at the same time, I will give you now the analogous version of our theorem for Drinfeld. So the first thing to observe is that now, if we use the same paradigm with the gradient shifter, my K matrix, so this would be simply, by definition, this is going to be my K matrix evaluated on the finite dimensional representation dz. This is going to be a format series, but this is going to be a function of this form. And this is fundamental that now my psi, you can think of it as being Chevalier. So if I'm Chevalier, this is really what I get. I take Vz and then I twist by psi, but then I pass it through Chevalier, and Chevalier is moving Z to Z inverse. So it's performing exactly this inversion of the parameter, which is fundamental for the reflection equation. And so our theorem, which then again was still 2022, published this year. So this is also saying that if I take a finite dimensionally reducible over the quantum group, then the first theorem is that Vz is generically irreducible over V. So it means I take a finite dimensional representation, I restrict it to the QSP, and then for all but a finite number of points, this remains irreducible over the QSP. Again, this is extremely unlikely if you think about it in SL2 even with respect to the other function. It's clear that actually it never is. And then the second theorem is that there exists a unique factorization of my KVZ as a function GVZ, KB rational. Actually, this is more the rational. This is polynomial. Maybe I will comment a bit in a second. And then where GVZ, in my case, this is just a formal power series. And with GV0 equal to 1. And instead, this guy is polynomial, but this is nowhere vanishing. There is no points where all the entries goes to 0. It just means that this polynomial have a common divisor equal to 1. Okay, so that just go right. And so this we said this is a polynomial operator. Fine. And then now if I have one condition, but then again it's similar to what Andrea said in his pre-seminar. It's like whenever let's assume for simplicity that psi is invisible, right? So in our case, psi is never invisible, but if I'm able to get some, so this is a condition, so if my module satisfy a condition like that, whenever I pull it back through Chevalier, I get something that I can control. This is similar to the opposition evolution up to a global shift for some A. Then, whenever tau is equal to the opposition evolution itself, this is again an example of a QSP that you can take. This is going to be the opposition evolution for the family part, I should have said. Then I get unitary solutions of the reflection equation as I wrote it before. It means the twist is indeed going to disappear, and then I get a honest solution of the reflection equation as I first wrote it on the board. So with no psi appearing and the right behavior of the parameter. Just a couple of comments. So there is actually another case similar for t equal to the identity. Whenever tau is the trivial involution, I also get solutions, but of a different reflection equation, which is called the transposed reflection equation, which appear also in physics. This condition is not particularly restricted. There are infinite families of modules that satisfy this condition. So actually, this is very common to find, but it's not true always. And the very last comment that you may have seen, I told you that for the R matrix, the factorization is actually given by a rational component, and then I have a meromorphic component. In my theorem, I cannot say that this scalar is meromorphic. In general, we are unable to find that so far, to find a good identity that allows us to conclude that this is meromorphic, but I can actually say that this is true for G equal S2. So for a fine S2, there is a trick that we can use, and actually this allows you to prove that this factor, which is in a certain sense is computable, is a meromorphic function, and is not a particularly easy meromorphic function. This is even on C2 tensor C2, so on representation of two-dimensional representation. What do you see for quantum of fineness 2? You see that this is going to be a rational function, so a ratio of polynomials times a ratio of Q-Pochamer symbols. You get something which is exists pretty standard compared with the theory of the R matrix, but this is something that yeah, even for S2 is a nice trick, but it works only for irreducible. We cannot prove it in general, and so we still don't know how the answer is going to be. But of course, we conjecture that this guy in general must also be a meromorphic function. And then I stop here. Thank you.
Done quite a bit over time. I think we'll just leave one quick question from online, if there are any, and those who are here can talk to Andrea afterwards. So that's the relevant and some else.
My questions as well.
There are no questions from online. I think we'll just end it here, and you guys can ask a question afterwards.
Thank you. Sorry for being late.
Let's thank Andrea again.
If you don't mind, I
Yeah.
have some questions.